Good morning, everybody. Thank you so much. Again, I'll just echo the comments from Janine and from the Herdman Society. Really lovely to see so many people here. Many of you probably already know me because you've either been lectured by me or are a colleague of mine or have seen me talk somewhere else. But for those that don't, as I said, I'm Dr. David McNamara, a geoscientist with a specialization in structural geology and mineralogy. Particularly these days with a focus towards how I can bend those two disciplines to better understand applications like how they influence the energy transition or net zero solutions. And that's a little bit what I'll talk about today. So some of what I'm going to show is quite new as well, which I'm excited to show it for the first time. It also means I haven't really thought about it extensively, so bear with me while I talk through some of these slides. Thanks. As with any good science, which I hope you'll agree with me, this is good science. As with any good science, it's never done by an individual. It's done by a team of many, many people. A few key people I want to point out here are Aisling Scully, and Aaron Lister and Gabrielle Pasquet, earlier career scientists that I've worked with, PhD students of mine as well, who have contributed significantly to the work I've done. I've actually just realized that Jonathan Alexander's not on there. I'll talk about him later. So, the title of the talk, Mineral Processes Impacting Geological Net Zero Solutions. So, let me first explain what I mean by those mineral processes. What am I talking about? What do we need to understand? So, there's a whole range of different atomic scale processes that govern how mineralization occurs in our geological systems. So, we have everything from nucleation processes. Now, this isn't working. So we have everything from nucleation processes, and there's a range of different types of nucleation processes. Minerals have to somehow precipitate from a fluid and bond to a surface in the subsurface, so minerals can then develop and grow into geological veins or pore space filling fluids. So we need to understand what those nucleation processes are. We have a whole different range of terms and observations that we've applied to these, but actually when you start looking into the literature and understanding of what we currently know about this, it's actually a little bit limited. We are still not completely sure exactly whether minerals like to nucleate on fracture walls through what we call heterogeneous nucleation, or whether they precipitate out of the fluids themselves as they move through these systems, so homogeneous nucleation. So, and we see evidence in natural examples that suggest both can be occurring. We also have pretty limited understandings of the nucleation rates of in these systems as well. How fast do minerals nucleate out of these fluids in these systems? Are they bonding to their substrates through epitaxy or topotaxy, through the crystallographic relationships between what's precipitating and what they're precipitating on? Do we have special orientation relationships? There's lots of questions around that nucleation point as well. Growth we have a little bit more of an understanding of because we've been observing chemical profiles and chemical zonation of minerals growing in systems for long periods of time. So we have existing models for how minerals grow and develop. Syntaxial development of minerals growing from the fracture walls inwards towards each other. Antithetics growth as it pushes outward. Crack seal, do we have staged growth? But again, we still have questions about exactly which type of growth that is in every particular system that we look at. We also don't have a great handle on the rates of mineral growth in different systems under different conditions as well. We have some experimental work that's given us insights into this, but there's lots more that needs to be understood because it's quite a sensitive, it's quite a sensitive value to lots of different factors. We also have to think about other processes that are going on, like growth competition. Why do some crystals outperform others whenever they nucleate and start growing? Why do some grow faster than others and some slower than others? Are we also dealing with pressure solution? As these things are growing, they're also dissolving and precipitating new things as well. So endless questions just on the nucleation and growth mechanisms that govern mineralization in the subsurface. Oh, sorry folks. Good grief. Okay. In terms of mineralization processes as well, it's not just the minerals that are growing in free space, there's also mineral alteration. So we have lots of different mineral replacements. As the conditions, temperature, pressure, chemistry of geological subsurfaces change over time, minerals like to replace each other as they try and establish themselves in some sort of near equilibrium type of setting. So we're dealing with processes like oxidation, reduction, dehydration, hydration. All of these different processes are acting at the same time in different spaces, in different, acting at different times in different spatial settings as well. So we need to get a good understanding of these things as well. So there's lots of other mineralization processes occurring in the subsurface. Then we have knowledge gaps around the mechanisms that control those processes. So nucleation, replacement, mineral growth are all controlled by lots of other things. Everything from the surface roughness of a fracture can have a significant impact on where minerals like to nucleate, or even the composition of the minerals that will nucleate and grow in those systems. Fluid chemistry, pressure and temperature is a significant control in mineralization in these systems. The supersaturation levels of a fluid significantly impact what type of mineral are going to drop out of those fluids in different places. Microbial activity has been proven to show, for example, enhanced carbonate growth and development in certain places as well. So there's a biological component to these geological systems that we still are only getting to grips with now. We're only just starting to discover the processes of. Organic compounds and their control and what chemistry gets bonded into some of these crystals is really important too. So lots and lots of really good and interesting knowledge gaps, which make it a very rich field for research. So we have a huge amount of information that we want to know and need to know about these mineralization processes. So I want to understand particularly how these mineralization processes are impacting our net zero systems. So our geological net zero systems, I'm going to speak about a few specifics here, and I'm going to focus today on geothermal systems. So geothermal power is something that we are looking to use more and more as we move towards a decarbonized future. We're looking to use geothermal for electricity generation. We're looking to use geothermal for heating, for agriculture, you name it. We can probably do something with geothermal. People are even brewing whiskey in Cornwall with it now. So there's lots of uses for geothermal energy. And geothermal energy is hot fluids traveling through geological subsurfaces, which results in mineral processes. So if we want to understand those geothermal systems properly and make sure that we use them correctly and use them sustainably, we need to make sure we understand what mineralization processes are occurring there. Ore bodies is kind of a self-explanatory one. I'm not going to focus too much on ore bodies today because we're going to get much better talks from other people on that later. But again, it's a mineralization process governed by fluid rock interactions in the subsurface, depositing the elements and metals and materials that we need. And in particular, with respect to net zero, we're considering critical raw elements, critical raw materials, things like lithium, cobalt, molybdenum, that kind of stuff that we're looking to develop our ever-growing need for green technology. And then I'm also going to look a little bit in this talk at mineral carbonation as well. So mineral carbonation being the process by which we inject CO2 into the subsurface. It chemically reacts with the rocks and minerals in that subsurface and then is bonded in solid form permanently. So it's a form of carbon capture and sequestration. In order to understand the mineral processes that are occurring in these types of systems, we have to bring to bear a lot of different techniques to it. And those techniques range from everything, for example, that our first years are learning about this year, which is using the petrographic microscope and understanding how to identify mineral type, mineral texture in the microscopes, all the way up to using some advanced scanning electron microscopy techniques like the ones we use here in the Scanning Electron Microscopy Shared Research Facility. So these techniques involve using electron beams to penetrate into various depths within a crystalline surface so that we can characterize various aspects of it. The particular ones that we use, or that I've been using, and I'm going to show you the results of in some of this research, are looking at energy dispersive X-ray spectroscopy, which gives me chemical composition of minerals that I'm scanning with an electron beam. Cathodiluminescence, which shows me variation, again in chemistry, but also sometimes in the microstructures of crystals that I'm scanning with an electron beam. And then finally, a technique that has spent a long time being developed and developing a lot of expertise here at the University of Liverpool since even before I did my PhD here back in the 2000s, is electron backscatter diffraction, which is down in that lower corner here, where we angle an electron beam at our mineral surface and it interacts with the crystal lattice and it tells us about the orientation of the crystals in there. So we have all these really, really great novel techniques that we can combine with really traditional and very useful techniques like petrography to really understand what's happening in our mineral systems. So, great. So geothermal mineralization is the first one I want to speak about. And this is a particular issue in geothermal systems because ultimately geothermal resources and their efficiency and their success relies on the ability to constantly transmit fluids through the hot subsurface so that we can keep cycling them through to mine the heat out of the subsurface or to use the heated waters and steam and dual phase fluids to drive turbines to create electricity. If mineralization is occurring inside these systems and minerals are nucleating and growing, they're closing up that open space that allows fluids to be transmitted through those systems. So understanding the nucleation and growth mechanisms in geothermal subsurfaces becomes a really critical component of understanding how we can operate those systems efficiently, sustainably, and make them last longer. If you think about the way that these mineral processes develop and grow in these systems, if you think about scaling as in your kettle elements, which develop mineral scales over them over time, or your washing machines or dishwashers, which develop coats of mineral scaling, it's the same sort of process we're talking about in geothermal systems. We're having fluid reacting with the rock around which they're traveling, dropping out minerals through those processes. So to explore this, we've looked at a range of different geothermal sites, both internationally and here at home. And I'm going to show you some results of some of the quartz scaling and quartz mineralization that we've seen, which serves to block up geothermal fluid flow pathways in the subsurface. So we're going to look at a couple of examples from sites in New Zealand. This is in the top corner here, this is the Taupo Volcanic Zone, which is one of the main geothermal producing regions of New Zealand. We've got the Coromandel Volcanic Zone, which is an extinct geothermal system, so it's an exposed roots of the hydrothermal geothermal system. We're looking at recent geothermal activity from a region in the Kibero geothermal area of Uganda. And then we're also going to be looking at some quartz veining that we collected from the granites in Cornwall, which are currently being explored and developed as geothermal resources for the UK. When it comes to quartz precipitation, there has been quite a bit of progress in understanding the progress of how quartz grows and develops in open spaces. So we start off by channeling a silica-rich fluid through a fracture space or a pore space, and over time, silica colloids inside those fluids start to bond together, they start to polymerize. We still don't know, however, despite knowing that that's what happens and that's how silica starts to bond together and form and the very early stages of quartz development, we still don't understand how those colloids then deposit themselves and bond themselves to fracture surfaces, to pore space surfaces. That's still a question that we have. Over time, the polymerization continues and it ends up developing these complex opal A or opal CT nano and micro textures, which as they mature, develop into lepospheres, which you can see here. So we're going from these nanospheres building up into these more intricate structures called lepospheres, which then, as it keeps evolving over time, develops into opal C, where we get these blocky nanostructures and nanorods, which I've got examples of here and here. And then eventually, with enough time, that opal C eventually transforms itself into crystalline hexagonal quartz. While we understand the process of this, and we've observed evidence for this process of quartz development out of silica-rich fluids, again, we still have questions around what those transformation mechanisms are. How do we go from something amorphous like opal, eventually turning it into crystalline quartz, and how do we unravel the history of that happening to understand how the very first phases of that silica actually started bonding to the surfaces that we're interested in. So this is a nice example from Cornwall. We went down into the field, we looked at some of the granites, and we collected some samples of quartz veins that are already precipitated, already formed, because then we can analyze the quartz in these systems and get a sense of how that quartz has developed over time, hopefully giving us insights to how it may continue to develop as we operate the granites in Cornwall for various reasons, all the way through from geothermal operation to actually lithium extraction through brine cycling as well. So we can cycle fluids through these granites to strip out lithium, which we then extract from using filters at the surface. So again, not keeping those pathways open is really important, not just for the geothermal energy perspective, but also from a critical raw element perspective, lithium being really important for battery development. So here's our quartz vein. If I just start off with a simple technique, which we've all probably used at some stage or another in our careers if we're all geologists, is a bit of petrography. So this is a thin section of that quartz vein cut across the vein here. So we're looking at these crystals side on, and this is just crossed polarized quartz. So over here, I've got my granite fracture wall. So this is the granite on this side here. And then I can see multiple deposits of quartz crystals as they move outward away from the wall, outward from that fracture wall, getting bigger and bigger and bigger as they grow outwards towards the center. So I can identify, just with microscopy, multiple events of quartz precipitation in this particular vein, including these blue lines, which are the progressive different phases of quartz that's precipitated, but also in green I've highlighted a number of subsequent crack textures that have developed and then been infilled with new quartz afterwards. So there's multiple events of quartz precipitation happening in this system. What I'm going to do is focus in on this part here because I'm interested in what's happening at the fracture interface, but also what's happening at the individual interfaces between each layer of quartz that's being precipitated in these structures, closing them off to fluid flow. Oop. So this is just a zoom in of that in cross-polarized light. So we take our thin sections, we put them into the scanning electron microscope, and the first thing I want to try and get a sense of is how have these quartz crystals developed with time? So I want to get a sense of any zonation, chemical zonation, which might give me a hint as to the way they've grown. So I'm overlaying that image with a cathodoluminescence image, which we captured inside the SEM of that same area. So this grayscale different shades of grey relate to different zones of quartz being precipitated with time. So for example, if we look at this crystal here, you can see nice quartz facet development in different bands of grey as the quartz grows outward from the fracture wall and into open space. Then we get to the end of that first generation of quartz precipitation, which is this very dark line of quartz here. Now that's not a gap or a break in between two generations of quartz. That dark line is quartz itself. It's just a very different cathodoluminescence. It's got different luminescence values because the chemistry of it's very different. So if nothing else, this information is telling me that as the quartz crystals grew, the first generation quartz crystals grew, chemistry was probably changing the fluids slightly, giving us the zonation patterns we're able to identify. But then at the end of this initial phase of quartz precipitation, there was a quite significant change in the chemistry. And then we have this interesting, dark, very non-luminescent quartz before the second phase of quartz takes over, which looks very similar to the first. So we're already starting to piece together a little bit of a story about how the chemistry might be, the chemistry of the fluids the quartz is precipitating from might be influencing the way these things grow. If we zoom in again onto this boundary between phase 1 and phase 2 of the quartz scaling, and I want to explore a little bit more this boundary in particular to see how there might be a relationship between these two boundaries. Now I'm going to move to a new technique or a different technique to try and get a bit more insight. So this very colorful image that I'm showing you now is a crystallographic orientation image. This is data. Every single pixel in that image is colored for the orientation of the quartz crystal lattice. So it's telling me the orientation of the C and the M and the A axes of that hexagonal crystal that makes up the quartz. What I want you to focus on is this long green and blue grain here. When I go back to the cathodoluminescence map, you can see that that single blue and green grain is actually covering that boundary between two phases of quartz precipitation, but the crystallographic orientation of that crystal is exactly the same. What this is telling me is, as I start to develop the second phase of quartz precipitation, it's actually using the quartz in the first phase as a template upon which to grow, which is a trick that geology uses quite a lot whenever you're developing mineralization. It will use existing templates to grow the same mineral on the same mineral because that's quite easy. It's a low energy solution for something to start precipitating. So what we have is a nucleation control on the second phase of quartz precipitation. So I'm getting heterogeneous epitactic nucleation mechanisms occurring in these systems, building up layers of scale as they go on. And again, this is just a graph showing me the crystallographic orientation across that boundary between the two quartz crystals, showing that there's very little deformation in that crystal as I move from one side of it to the other. There's very little evidence that there's any difference between the crystallographic orientations of those two crystals. They are, for all intents and purposes, the same crystal because one has built itself on the other one. We see this in other data sets. So this is an example from a quartz vein in a geothermal system that we drilled and cored in New Zealand, the Ngatamariki geothermal field. And here we have a nice cathodoluminescence image of the quartz vein here. And you can see different zoning showing me how the crystals are growing outward from the fracture wall and into the middle. Whenever we do the same electron backscatter diffraction mapping, so I'm looking at the crystal orientations, I lose the edges, the nice sharply defined edges of that vein. They disappear in the crystallographic map, again, because the quartz in the vein is using quartz in the wall rock of the diorite that it's growing in to establish easy nucleation mechanisms and then develop very easy quartz growth. So again, not only is individual layers of scale using previous layers of scale to develop, it can actually do this off the fracture wall if there's quartz in the fracture wall as well. So we're getting some really interesting insights now into the nucleation mechanisms. It doesn't always work like this. So this really amazing image here is some data that was collected by Aisling Scully, a PhD student working with me on this. And you can see there's two quartz veins here. The red one is crossing this sort of more green and blue one. And what you're seeing here are long crystals that are growing fast along their c-axes inward. And quartz really likes to do this. It likes to grow rapidly along its c-axis. It's its preferred growth direction. And we can see it growing into the open space from either side in this vein and growing either side into this vein. That's why they have different colors, because they're in two different orientations crystallographically to each other. What gets really interesting then is when we look at the center here, where the quartz coloring starts to go a little bit off. We don't have these nice, easy red crystals, which are showing me nice c-axes this way. Instead, we're getting a bit of a jumble of crystal orientations in the center. And this, despite quartz liking to nucleate and grow with its c-axes outward into open space, potentially it's now trying to use some of the quartz, the pre-existing orientations of quartz to nucleate and grow here. So we're getting a competition of different nucleation mechanisms happening in the center here. Something else that you might notice, if you look to the side here, there's a little black strip just at the edge of the fracture wall. If I zoom in on that, what you can see here is there's a black area where we don't have the orientation of that mineral, but we do have the chemistry of it. So this black area is a mineral called jarosite. It's a geothermal sulfate that's formed at the edge of the fracture wall. And when we look at the quartz next to it, there's multiple tiny, tiny, tiny crystals, which is very different to what we see in other areas of the fracture wall, where we see large crystals starting at the fracture wall and growing out. So what we think in what we're observing here is the presence of that mineral, that sulfate on the fracture wall, actually makes it very difficult for quartz to nucleate there. So we end up with lots of small multiple nucleation points, which generates this microtexture in quartz at the side, meaning that this part here takes a long time for nucleation to happen, but also for quartz to keep growing. So anything lined with the sulfate looks like it actually prevents quartz precipitation, or at least inhibits it to a certain level. It doesn't make it easy for the quartz to grow, which is quite interesting for us when we come to think about these events. When we look at other veins as well with other minerals in them, jarosite isn't the only thing that seems to influence the way quartz develops. This is two different maps here. So this one at the top is a phase map telling me what mineral I've got in my vein. So the blue is quartz, and the green is a hydrothermal plagioclase called adularia. So the adularia formed most of the way along the fracture wall first, and then quartz developed afterwards, filling in the rest of that vein. When we look at the orientations of the quartz, which is all this colored map down here, so these are the different orientations, we don't see any consistent orientation pattern, nor do we see those nice textures that we were seeing in the vein with the long crystals growing inward. What we end up with is more of a blocky texture, so we think the adularia is having some sort of effect on the quartz development and growth in a different way to the way it would normally grow if it was bonding to quartz in the wall. Aisling, when she started looking at the individual grain boundaries between adularia and quartz, discovered that there's a very common relationship between and this is what I was talking about earlier with these special orientation relationships. She established that there is a common angle that the A-axis of quartz likes to bond to the A-axis of the adularia in a very specific manner. And she found this in samples from Uganda, she found this in samples from 2 areas in New Zealand, and in a sample from Iceland. So everywhere we get adularia, followed by quartz precipitation, the adularia actually causes the quartz to nucleate in a very, very specific way and in a very specific orientation. So again, we've discovered another effect or another nucleation control on quartz precipitation in these systems. So summarizing just that little bit about the quartz, correlative microanalysis, so using petrography, using SEM techniques like photoluminescence and electron backscatter diffraction to capture multiple types of information about minerals, give us really great insight into their nucleation and growth mechanisms. We can already identify heterogeneous epitaxial nucleation, progressive quartz nucleation and growth, potentially being easier and faster as it bonds to pre-existing quartz. Heterogeneous topotactical nucleation, and this is just different ways that different things grow in each other at different angles. And then nucleation and growth of large crystals being hindered by things like the presence of jarosite on the fracture walls, for example. So we're able to establish a few different controls on the nucleation and growth. And this is important for us because if we can start to understand what inhibits and what encourages that quartz development, maybe we can start to come up with techniques that allow us to influence quartz precipitation in the systems, the net zero systems that we're interested in bringing online, like geothermal systems, making them last longer, making them more sustainable, making them more economic to operate. Moving on to a totally different system now, and this is really exciting work that I'm happy to present for me for the first time. This is work that's been done by a master's student who works with me in the National University of Ireland, Galway. Oh no, University of Galway now, they changed their name. This is Jonathan Alexander, and he's been working with me on a project to understand Ireland's potential for mineral carbonation. So that's the process by which we take CO2 and capture it at a source point. We combine it with a fluid. We then channel it to an injection site, and we use a well to inject it into a rock, where that CO2-rich fluid will interact with the elements in the rock. It will hopefully dissolve out cations like iron and calcium and magnesium, and then the CO2-rich fluids will bond with those and form carbonate minerals. So essentially what we're doing is turning CO2 into rock. It becomes a permanent storage solution for CO2. And this is something that they've had a huge amount of success with in Iceland through the CarbFix project, where they've managed to store significant volumes of CO2 at consistent rates in basalt formations, and that has now been expanded out to projects in the United States and in at least 3 or 4 areas across the rest of Europe. So part of a research project that we had funded jointly between the University of Liverpool and the University of Galway was to explore the whole of Ireland's potential for carbon sequestration, both traditional storage like in saline aquifers offshore, but also whether we could find lithologies in Ireland that would be suitable to repeat the CarbFix experience. And this was funded by the Sustainable Energy Authority of Ireland. So most of the way this has been successful so far is when we do the capture and injection onshore into basalt rocks that are rich in minerals that have those divalent cations like calcium, iron, and magnesium. There is interest now in developing this offshore, mainly because if you think about the ocean crust of the Atlantic, for example, it's completely made of basalt. So there's huge potential for storage, this type of storage to be done if we can make it possible offshore as well. But obviously there's issues with that. So what we started off with in Ireland was doing essentially a screening and ranking process where we identified a range of different lithologies across the country that looked like they might potentially be suitable for this type of carbonation process. And we came up with a list of criteria that we would rank them by and giving them score, and basically came up with a scoring system for this. So some of the criteria we're interested in is the original mineralogy of those lithologies. Again, we want minerals that are rich in iron, magnesium, and calcium. So you get more points if you're an ultramafic rock, you get less points if you're intermediate, or if you're a northite, your plagioclase northite is less than 50% northite. We then look at the alteration of that. Alteration can either enhance a rock's potential ability to interact with CO2 fluids or decrease its ability to do that, depending on what type of alteration you get. For example, if you're getting a lot of albitization of your rock, you're stripping a lot of the calcium out of it and leaving a lot of sodium in there, so it reduces the amount of calcium available for a reaction with a CO2-rich fluid. Then we have other things like the surface area and the thickness of those units. If we can work out those, you can work out how much volume of rock you have that might be potentially able to interact. The more, the better. Something that's really useful is then what proximity does that lithology or outcrop have to CO2 sources. It's great to be able to have a rock you can inject it into, but if it's kilometers and kilometers and kilometers away from where the CO2 is being generated, then you have to start to think about the techno-economic issues of transporting that CO2 in a safe and useful way to the injection site. Proximity to urban centres is important to think about as well. If it was, again, you need to think about the social license of developing this kind of thing in different types of areas, and whether local people will be receptive to the idea of injecting something into the subsurface nearby. Other aspects that we needed to consider were the fracture or basically the permeability of those rocks as well. We're dealing with crystalline rocks for the most part, some of which are notoriously impermeable, but we need to assess whether or not they can actually take injection of fluid into them or not, and actually have surface areas for that CO2 fluid to react with. Other things like distance to water, the existence of aquifers. Again, you don't want to be polluting groundwater systems. So we developed this and we scored a number of lithologies. This is just to give you a little breakdown of some of the mineralogy and how that was scored as well. And you can see the higher scoring points of places like Deer Park Complex. We have the Antrim Lava Group down here, and the Connemara Metagabbros, and a few others as well. So on some ranking criteria, some lithology scored very well. In other ranking criteria, they scored less. So when you tally all of that up and you come to a final conclusion, we were able to identify the two most suitable areas for testing out mineral carbonation in the island of Ireland. We identified 30 different groups of potential reservoirs. The top two that came out, the first one was the Paleogene Antrim Lava Group, mostly made up of tertiary basalts, and a very extensive outcrop as well, with significant thickness in areas. So this is our low-hanging fruit in terms of doing this in the island of Ireland. And the second area that came up in terms in number 2 in the ranking was the Connemara Metagabbro and gneiss complex, where we have orthoperoxenites, peridotites, and metabasalts and metagabbros. Interestingly, number 4 in the ranking were really, really suitable from a geological perspective, but they are located in what's known as the Copper Coast UNESCO Global Geopark, which means that there's absolutely no way they'll be injecting anything into that region anytime soon. So we had to eliminate what was a potentially very suitable site for this type of project because of the social license of doing something like that in a protected region. Just to zoom in a little bit on both the Antrim Lava Group and the Connemara Complex. The Antrim Lava Group, again, coming out on top, thank you very much, I might have to speed up a bit, coming out on top because it's bigger and it's very closely located to some major CO2 sources like a gas power plant, for example. Whereas the Metagabbros down in Connemara, while mineralogically very attractive from a carbonation perspective, are very, very distant to any real major sources of CO2, so the transport becomes more of an issue. So we had to do a bunch of work in this MSc to do a little bit more research to understand the mineralogy of those two systems. So we did a bit of field work. So we got to go and look at the Giant's Causeway, which was nice. I always like going there. And we established some observations based on the mineralogy and the texture of the rocks. So what we can see is there used to be a lot of large open spaces in these basalts, but they've been subsequently filled by minerals known as zeolites. So there's maybe a permeability issue with some of these rocks in terms of the amount of fluid rock interaction that's already happened through the geological history of the Antrim Lava Group. So we have to consider that as a potential inhibitor for these systems. Really nicely, though, however, we were able to access some of the core thanks to the Geological Survey of Northern Ireland, who are associated with this project and have been very helpful throughout the process of it. And we were able to sample some of the basalts from depths that we would be interested in injecting something into if this ever became a reality. And what you can hopefully see is there's actually quite a large amount of white mineralization happening in fractures in these basalts, as well as in the vug and pore and vesicle spaces in these systems as well. So we are dealing with a permeable network that has quite likely been in lots of areas significantly mineralized. Going into Connemara, we actually got amazing weather. It's the first time I've ever done any fieldwork in Connemara where I haven't got wet. And we actually got to access some areas that you normally would be knee-deep in bog. But we were able to get really great samples of a range of different lithologies, orthoperoxenites, serpentinites, peridotites from those regions that we could analyze a bit more. So we wanted to look at the mineralogy of these. So again, we're just going to use, at the base level, we're going to use some petrography. So we can see in our basalts in the Antrim Lava Group, we have a bit of chloritization alteration going on, which may or may not be a good thing. It's again, chlorite contains a lot of magnesium. That is an element that we're interested in. But what hasn't been really explored a lot yet in the research is whether clay minerals like smectite and chlorite and that will give up their magnesium to react with CO2-rich fluids, which is something that needs to be explored a bit further. When we look at the minerals we traditionally consider as part of these carbonation reactions, the olivines, you can see that in some places the olivines are very fresh, so and they're magnesium-rich. So we've got nice forsterite olivine. However, they are rimmed by Iddingite materials, so there is some alteration around the edges, and that Iddingite might be a barrier to access for the CO2 fluids to access the magnesium inside the rest of the zeolite. So we have to consider these things as well. We actually then went a bit further to identify some of the zeolites that were growing in these open spaces. So we have things like chabazite and thompsonite, which are interestingly, some of which can be calcium rich. So that does open up this idea of, even though they're filling up all those spaces, they're a calcium rich mineral, which might be really useful for interaction with CO2 fluids to form calcite, for example. So it could be a carbonation, potential rather than a hindrance. And then we have a whole range of amphiboles, peroxenes, orthoperoxenes in some of the metagabbros, which are suitable in terms of their cation content for carbonation. We look a little bit more at these are the orthoperoxenites, and again, you can see that there is some alteration that's already undergone in these things. These things are fractured and shattered. They have been altered for a while. And then we also looked at some of the sort of more serpentinized material as well. So there has been quite a bit of alteration. There has been quite a lot of processing happening. What we also found in some of these systems is the presence of carbonate mineral formation as well as carbonate veining. So some of these rocks in the Connemara region have actually already undergone a natural process of carbonation. Carbonate minerals have been forming in these systems over time, probably due to some interaction with CO2-rich fluids throughout their history. We then go in with energy dispersive X-ray spectroscopy, which allows us to identify chemistry in the scanning electron microscope. And again, we're looking at the differences between more fresh olivine and more altered olivine, and you can see that the magnesium content in fresh olivine much higher than in the altered olivine. We're seeing some of the magnesium being stripped out whenever the olivine is more altered. So it shows us that olivine usefulness for carbonation actually varies spatially depending on where you are in the Antrim lava group, and that's something that might need to be mapped out in order to know exactly where is best to inject the CO2 if you ever want to do it. We then mapped out our zeolites in some of these systems, which show really nice high concentrations of calcium in them, and to a lesser extent some magnesium as well, again making them potentially useful for carbonation reactions. And this is a point of ongoing research about whether or not zeolites do make good carbonation minerals. We did some chemistry on the Connemara rocks as well, showing again high levels of both magnesium and iron, and to a lesser extent calcium, in the more fresh samples that have been less altered. But when we move to the more altered stuff, we see particularly decreases in the calcium as albertization alteration starts to take over in some of these systems that have been subjected to more fluids over time. So, summarising this, we have a really good ranking scheme that has helped us identify Ireland's best potential for carbonation or to test mineral carbon sequestration. The Antrim Lava Group ranks really high based on multiple criteria, from the size of its lithology to its mineralogy to its proximity to CO2 sources. Alteration in the Antrim Lava Group limits its potential, but we do think it varies spatially. So we need to do more research to actually fully characterise how that potential for carbonation has changed with time. Zeolite precipitation, though it has maybe inhibited the amount of permeability in these systems, might actually be a suitable mineral itself for carbonation. So if we can reopen some of those spaces and inject CO2 fluids into them, they might react really nicely to serve to precipitate new carbonate minerals. And in the west of Ireland, while the Metagab was an ultramafic seam, very suited for carbonation due to some alteration processes and the occurrence of naturally occurring carbonation in those rocks, their potential might not be as high as we originally thought based on our research. How much time have I left? Okay, cool. So that's a study that we've just finished. It's just been written up by the master's student, and hopefully he will be starting a PhD with us here in Liverpool to expand this further, because we now have industry in Northern Ireland interested in testing out local carbonation sites, local basalt sites as potential CCS sources for local producers. So trying to establish local solutions for local CO2 or emission problems. And again, enhancing the use of those local and small scale, potentially, net zero geological systems. However, like I said, there's an idea between people in Iceland and other people that are interested in this carbonation process about whether we could do this offshore or not. Recently, I had the pleasure of being invited on an International Ocean Discovery Programme expedition. Last summer, I spent 8 weeks at sea in the middle of the Atlantic Ocean, drilling a bunch of basalts out of the Mid-Atlantic Ridge, with the idea that I would explore the alteration of these. So this is the ship, the Joydes Resolution, that I spent 2 wonderful months on. This is some of the core that we extracted from some of the basalts there. You can see some beautiful mineralization happening in these systems. So this is where we went. We were drilling here, this little transect across the Mid-Atlantic Ridge. Here's the ridge itself. You can see it kind of forms a V shape. So we drilled a number of wells, moving further and further away from the axis, getting a little bit older as we moved away from it. So we have core that's core of oceanic crust that's about 3 million years, all the way out to 33 million years. We also drilled another site out of here, but we weren't getting basalt from that. We were more looking at the sediment deposits. And there was a whole bunch of scientists out there. There was about 25, 30 of us, all with different research goals and different ideas about what we were researching. Some people were trying to establish what the nature or processes are that control the formation of these V-shaped ridges that we were drilling. Some of us were interested in the alteration that happened there, because in these regions, there's quite a significant amount of hydrothermal circulation. Hot fluids circulate around in these systems quite a lot, and they're responsible for significant components of global element cycling, including carbon cycling. So from my own perspective, I'm interested in how much natural carbon gets stored in these systems, and how much potential may there be to put more carbon into those systems and lock it up permanently to help with carbon cycling. And to do that, we had to answer a whole bunch. This is our current conceptual model, published by Rosalind Coggan and Damien Teagle. And you can see that despite having a really good idea of the concept of how these hydrothermal processes work out there, we have a huge bunch of unanswered questions, which our data sets were able to help with. And this is some of the very earliest data. I've not shown this to anybody before, so you're the first people to lay eyes on this. So we can see here's the intensity of alteration as we move from the ridge out to the flank. And you can see the increase in this dark blue shows the increase in the amount of core, the volume of core that was completely hydrothermally altered. And you can see that there's a little bit of variation as we move across the troughs and ridges of the V-shaped ridges, but it's quite weakly altered for most of it. And then as soon as we get out to the flanks, the alteration jumps up quite significantly. Over in this graph here, this is the percentage or the volume percentage of core that is comprised of vein minerals. So for example, when we get out to the flank site here, so this is our furthest site over here, nearly 40% of the extracted core that we got from the basalts is comprised of vein minerals, predominantly carbonates. So there's quite a significant amount of natural carbonation has happened in these systems already. However, when we look at some of the textures of those veins, we see that they're reactivated multiple times, which means that you can keep fluids moving through these systems more than once, which means there still might be potential to introduce more CO2 to those places. However, as we come back towards the axis, we see that the amount of veining volume drops off significantly, and we see a significant drop in carbonates. So making potentially the sites closer to the ridge axis more attractive from a carbonation potential if we ever thought about doing this offshore. But also we're getting closer to a site where there's a lot more seismicity, which means more seismicity means more fracturing, means increased permeability. So it might be easier to even inject the fluids, and also less sediment to drill through to inject the fluids into it, shallower sea levels as well. Makes the axis sites a lot more attractive from a potential industry development perspective. And again, we're just thinking about the geology, or not thinking about the multiple other issues we'd have to consider if we were ever going to do this offshore. But we're establishing and we're filling in some of these question marks on the conceptual model that are going to help us decide whether or not it is worth a pilot study to inject offshore. We looked at some of the alteration of the minerals in thin section while we were on the ship. It's really interesting trying to do petrography with the ship whenever it's rolling up and down. The focus does not like to stay where it is. But we can see that some of the basalts do have surviving olivine, although some of it is replaced by clay, particularly saponites. And we see a lot of celadonite formation in these systems as well, which is a specific type of mica that forms in a lot, this beautiful blue mica that forms in a lot of these subsea basalt formations. We're logging variations in alteration and the style of alteration with depth as well as spatially across the ridge and the flank. So we're getting an idea about if you drilled deeper, would you get into fresher basalts? We're looking at how the veining in the existing veining has leached and altered the wall rock around the structures as well. So again, that's useful for us to know if we're going to try and put more CO2 along these fractures, what's already been extracted as an aspect of the leaching of the existing alteration, and what mineralogy might be left behind. We're also looking at the fractures and charting how the fracture densities change with space and with depth in these systems. We've got huge amounts of data sets. We know that there's a lot of faulting from seismic data, so we know that there are fluids able to still penetrate all the way down from the sea into the basement, despite being out at crust that is under nearly a kilometre thick sediment. And we still know that seawater is able to make its way up and down through that sediment package and into the basalt. We're using, we've collected, thank you, we've collected a lot of samples, which are currently littering my office, and we've started to thin section those and look at these. So this is an example of one of the freshest basalts. So this is from one of the sites closest to the ridge axis, and this is one of the carbonate veins that I sampled from that core that we drilled there. And we can see these really interesting calcite growths inside this vein. They kind of have orbular radial patterns to them. This is not something I've seen commonly in hydrothermal calcite before. I've seen many textures, but I haven't seen this texture. So now we need to go in with those techniques that I was showing you earlier on quartz and apply them to calcite to see if we can better understand what the nucleation and growth mechanisms are in this particular system in the subsurface. And then we're also looking at the chemistry of the minerals that are filling in the pore spaces, trying to get a sense of how sharp these changes between different minerals are by using high-resolution electron microscopy, mapping the chemistry of these, and we know that some of these clays are very magnesium-rich. So again, we might be able to interact CO2 fluids with those clays, although that is something that still needs to be researched and investigated to see whether it's successful. And we can also see a range of different zeolites, again, which might, like the basalts in Northern Ireland, they might have that calcium-rich potential to be activated as carbonation minerals too. Summarizing some of that, we have this huge and amazing data set that we've extracted from the Mid-Atlantic Ridge samples, logging data, all sorts of measurements that were made on the ship, physical properties, you name it, we measured it. It took 2 months, but we have this fantastically huge data set, and there's some really, really interesting scientific questions, including the one I've just discussed, that we're trying to move forward with that. So final thoughts to everybody here. Just to summarize what I'm kind of getting at, mineralogy is a really crucial field of study when it comes to net zero. We need more mineralogists, and we need to push the boundaries of what we can do with mineralogy. We need to hone our techniques, and we need to make sure we're adapting and constantly utilizing new ways of looking at minerals so we can understand the processes that form them and that cause them to occur in our net zero systems. And despite decades of mineralogical research, there's still lots and lots of unanswered questions, which I've hopefully highlighted some of them to you today. Modern mineralogy has lots of new analytical techniques that can be used to help us deliver that new science and will aid the discovery, development, and operation of those net zero systems. And that science, that type of work is going to require earth scientists, future earth scientists like many of you sitting here in this room, to become trained in both the old and the new techniques, because they need to be used in concert if we're going to do this right and we're going to do it effectively. So there's so much to find out, which makes it very exciting, and there's huge potential for people to get involved in this. Thank you very much.